Hello everyone. So this is the first video for the series for learning R for business statistics. So in this first video, I would like to go over some of the basic functions in R and how you set up your working directory, and also getting to know some of the external packages for descriptive statistic analysis. So as you can see, I have the R Studio open here, and the first thing I think every time you're trying to do in R is to find out what your current working directory is so that you can actually load up the data in your project. So the first line right here that you can see, I'm going to run get wd functions. This is basically a function that shows you where your current working directory of this file is. So if you run this code, you can see there is a working directory, a path in your computer that tells you where your file is right now. If you are not in the folder or directory that for your current project, let's say you want to change your directory to somewhere else in your computer, you can also find the directory on in your folder and trying to copy that and paste it into this code. So all you need to do is to use the setwd functions. So setwd. Well, one thing very careful, because the function only read text into the functions, so you have to use the double quote or single quote to identify the path. So for instance, I'm going to set my working directory here, the C drive, under user, and the username, and desktop, well, in the teaching folder, and St. Mary College. And I have a folder inside St. Mary College, which is BUSAD40 for 2020. So if I run this code, I'll be able to set the working directories to this path. But one thing, very careful, you have to actually change all the strokes back to a backstrokes right here. So the reason is because I'll actually read the path different to your computer. So you have to change all this slash to a backstrokes. So there you go. So now that I'm in a working directory, and you can actually run the code earlier before and see if you're in the right path. So obviously I'm actually in this path right now. Well, let's say you want to actually reset your working directory. You want to actually go into the folder within this folder. So you can actually continue to type. So I'm going to go back to Business Statistics with R. And I'm going to run this. And you reset your working directory. And you check again. Now I am in this folder in my machines. So again, it's very, very important that you have to check your working directory and see if you are in the right folder in your machines to run your code, because sometimes when you're trying to run the data in a particular folder in your machines, you have to identify the correct locations. Well, the next thing that I would like to give you an idea is to import libraries in R. R, it's a very basic programming language. It has some very basic functions that you can use. However, most of the time we actually need to use an external package that is written by a third party. Just like using a different app on your window. Window has many functions that you can use. However, sometimes when you're using a different, you want to do something else, and someone designed that function for you in an app, you have to download the app and call the app to use it. So one way to install a package in R is to use this function right here. If you don't have the LSR package installed in R yet, you can actually do this code, install.packages, and then double quote or single quote with the package name, which is LSR. Well, you can run this function and automatically it will install to your R environment. Well, once you install the package, then it's going to be in your machines. So every time you want to use it, just like you double clicking on your applications in your machine, in your computer, you have to actually let your computer know you want to use it. So how you're going to do this in R is to use this function, library, and then you put in the package name, in our case, LSR. So you run this, and now the package is loaded up, so you can actually start using it. Well, without using this code right here, you are not able to import the library to R to use it. So you won't be able to use all the functions it's defined in this package. Well, in this demonstrations, we are going to use some very simple data sets to basically run some descriptive statistics. So the first thing that I'm going to do is to use a data file called afl_small.our datasets. It's actually coming from the data folder in the files. So I'm going to use the function low. So this low function only works if the data is saved as a R data format. So as you can see, the ending of this file, it's R data right here. If you are trying to load other types of data or other formats of data, for example, a CSV files or Excel files, or maybe even retrieving data from a different data formats like stata formats, you have to use these different functions. So the load function only works if the data is already saved as a R format. So in the data folder, I already have a groups of data you can actually use for examples. So I'm going to load this data. As you can see, I actually have two variables loaded up here. So one is the afl.finalist, and the other one is afl.margins. Well, you can actually check the variable here on the right hand side upper windows. However, if you are not sure about what is being assigned in your global environment or in your current workspace, your projects, you can always use these functions in R called who. So who function actually tells you what are the variable it's currently in your global environment or workspace. So if you run this, it will tell you you have two items or two objects here. So one has a size of 176 observations, and the other ones here actually have a size of 40 observations. So one is in numerical values and the other one is in vector. That means, well, it's actually a character. It's a string variables. Well, to see the data, you can actually use the simple basic print function. So for example, I'm going to use the print function to see what is in afl.margins. So I run this code and I see a list of number. So we have this list of number that telling us the winning margins of the games in this sequence. Well, you can actually use all these loading tools for the initial assignments. So the first assignments actually give you very basic problem to solve. So you can actually use this basic function to set up your working directory, loading up the library that's necessary for your assignments, and try to load some data if it's required in the assignments. Now I would like to show you some of the basic functions to do the measurements of central tendency of the data. Since now we have a data that has a sequence of numbers, if you want to actually calculate the mean, the average values of these numbers, you can actually use this very useful functions, the mean functions in R. So all you need to do is to type out mean, and then you put in the objects, the data objects into these functions within the parentheses, and you run this. It will return an average values of all these 176 numbers. Well, if you want to find the medians values, you can also use the median functions here. Well, the same thing, the syntax is the same. All you need to do is to pass in the objects, the data object here, the AFL.margins, and you run this code, and it will return the median of the data, which is the middle points of the sequence. Well, there are some very useful functions you also want to use to get some central tendency calculations. Unfortunately, the basic OWL do not have the mole functions for you to find the mole of the data. Instead, if you're trying to find the mole values of the data in OWL, you might actually need to find them by using the table functions. And you don't actually get the mole in returns immediately, but you have to check which number actually the most frequently happens in the data. So let me just show you the table function here. So in this table functions, I'm actually trying to check which finalist team actually appeared the most in this data set of AFL.finalists. So in this case, the table function returns the team names and the frequency that actually happened in the data. So there are 26 of this team, Adelaide, and for Brisbane, there are 25 times that happens in the data set. Carlton's appear 26 times in the data set. And remember, we have the finalist data set has a total of 400 observations. So each time when a name show up in the data, it will count the frequency of it. So basically, you have to check visually in this case to see which one happened the most in the data set. And in this case, the mole of the finalist data set is Gitlon. So Gitlon actually has 39 times to be the finalist in this data set. Well, option 2 is to use the external functions. Again, this function here called mode of is not a standard base OWL function. It's actually a function coming from the LSR package. So without loading the library earlier, let's say if you do not load this library, unfortunately, you will not be able to use this function here. Well, let's see what it returns. So I'm tracking the mode of the data sets finalists using the mode of, and what it returns, it's basically the name of the team that actually most frequent happens in the data set, and it match with our early observations using the table functions. Well, not only you want to check the mole and mean and median, sometimes you want to actually be a little bit more precise and trying to get something that we call a trimmed mean. A trimmed mean basically is a mean value that helps to take out the outliers in the data set and focusing more on the central tendency values. So for example, I'm going to create a new data set that contains this number here. And as you can see, I have one very extremely small number, -100 here, that obviously it's going to drive the mean value to be a negative number. Consider we have most of the number in the data set, it's a positive one. So if I'm going to assign this list of data to data sets variable, and I run the mean functions with it, I will get a -4.6. So obviously this outliner, -100 in the data set, is driving the data to a very extreme value. So it's not reflecting the true mean of the data sets, because most of the data actually belongs on this side of the x-axis. Well, to trim the outliner, well, what you can do is basically use this parameter in the mean functions. So to calculate a trimmed mean to take out 10% of the outliners in the data sets, you can actually use the parameter trim, and you set it equals to whatever proportions of the outliner you want to take out. So in this case, I want to actually take out the 10% of the outliner in the data set before we calculate the mean values. So I'm going to run this. And in this case, it returns the value 5.5. And obviously, this is the reasons why we use the trimmed mean instead of the regular mean, because the regular mean, it has this very big influences from this outliner, negative 100s. When I trim the 100s out, well, you can see that I have a mean value that it's much more reasonable to fit this data, where majority of the data are actually on the positive sides. Well, another important statistics that you usually will calculate in descriptive statistic analysis is the variations of the data, which is the variabilities. So there are quite a few measures of variabilities in the study of statistics. Well, one quick way to discover the variability in the data is to calculate the range of the data. So by definitions, the range of the data is basically the maximum value in your data minus the minimum value in your data. So to get the maximum value in your data, you can actually use the max functions from base R. To get the minimum value of the data, you can actually use the mean values, mean functions from base R. So you can actually run these two functions, and you get this result. The maximum value from the data, the margin data, is 116, and the minimum values in the margin data is 0. So subtract 2, you will get the range of the data. And obviously, if you do not want to do the math, you can actually take advantage of the base R function called range. Range is a function that actually calculates the difference between the maximum value and minimum value in a sequence of data. So let's run this, and it will return 0 and 116. So it returns the minimum value and maximum value all at one time. So you can actually get a sense of the range of the data. Well, another important measures in variability is to find the quantiles of the data, and trying to find out what would be the range within this quantiles. So to get the quantiles of your data, you can actually use the Quantile Functions. Let me run this. As you can see, well, it actually breaks out into the 4 quantiles measurements. So you have from 0 to 25%, and to the 0% of the value, the lowest value in the data is 0. The 25 percentiles value is 12.75. The 50 percentile value is 30.5, which is your medians of the data sets. And 75 percentiles is 50.50, and the largest value, which is the 100%, right, the top value, it's 116. So that gives you a sense of how your data actually break out into quartiles in the study. You can also just get a particular percentile or quartiles of the data by using the props parameter here. So let's run this and see what you get. So if you put in 0.5, that basically return a 50 percentiles value in your data, and in our case, which is the medians of the data, 30.5. If you only want to get the 25 percentile and the 75 percentile, you can actually use the same parameter props, and this time you can pass in a vector of what the values of the percentile you want to get. So this time you want to get 2 numbers. One is 25 percentile and the other one is 75 percentiles. So it will return the particular values at that percentiles or quartiles values. You can also calculate the interquartiles range by using the Iqr functions. So this Iqr function, it's going to get you the difference between the 25 percentile and 75 percentile difference. So that means we are using 50.50 minus 12.75. So let's see what we returned. So the difference between two, well, we have the range, which is 37.75, which is the interquartiles range. Well, there are other variability measures here. One particular that someone can use to calculate the variability in the data is called the mean absolute deviations. So in this case, we are going to use this very simple example. Let's say I'm going to store this 5 data points into a variable x. I want to calculate the mean absolute deviations of this 5 number. So the first step you want to do is to first calculate the mean values from this 5 data points. And I'm going to store this into a variable called x bar. Well, the next thing is I want to actually use every value in x minus the average values from the data sets. And then I'm going to put the absolute values sign to wrap this calculations. So every time when we have a calculations of this 2 difference, I'm going to turn this number into a positive number. And I'm going to assign this sequence of number into what we call AD, the absolute value numbers. So you might actually wonder what this AD actually looks like. Well, indeed, it's going to be a sequence of a vector of numbers, of 5 numbers, because there will be 5 numbers each time I'm going to subtract the average of x. So let's print AD to see what it looks like. So here you go. This is the absolute difference, right? The absolute value difference between the mean bar and every observations in our data sets. And the final step here, it's basically calculate the means of this difference, right? Since every number here is a positive number, we're going to add them up and divide by 2. So calculate the mean, and the absolute mean deviations will be 1.68 in our case. Well, to calculate the mean absolute value is somehow interesting to see the variations of the data. However, I would say it's probably not the most common type of deviations or variability measures that we use. In fact, if you want to use the LSR package, you can actually save all your time to follow this step and basically just use the AAD functions from the LSR package to calculate the absolute mean deviations. And see, we have the same results. Well, what's more popular to use in a variability measure is the variance of the data, or maybe the standard deviations of the data. So to calculate the variance of data, we basically follow the similar step as the absolute mean deviations, but instead of doing the absolute value, we are going to actually take a square of the difference between x and x bar. So again, I'm going to store the mean value of x, which is the data set we use right here, into x bar. The next thing we're going to do is basically storing the square deviations. We are going to use every observations in the data sets minus the average value of x. And this time we don't take absolute value, but instead we square it. Well, once you square the number within, even though the deviation is negative, it will turn into positive, because negative number times a negative number will always return a positive number. So you will get a square deviations in this case. So I assign it to a sqdiv variable here, and the next thing I want to do is basically calculate the mean of this square deviations. So I'm going to pass on the square deviations into this mean function and store into a variable called VA. And the result here is 4.24. So this is a square deviation distance in the data So that's why you will expect to have much larger value comparing to the one that we never actually square it, right? So when you actually using these steps to calculate the variance, just want to give you an idea that we are actually calculating the population's variations or the population variance because the mean function will take considerations of the sample size, and in our case, which is 5 observations. R actually has the base R actually has a variance functions, which is called VAR functions. If you pass in x, the 5 observation into these variance functions, you will also get the results here that it's very close to what we got earlier. However, this time the result is much larger comparing to the previous one. Well, you might wonder why the variance of the functions VAR will get you a different result comparing to the step-by-step results. The reason is because these variance functions in R actually calculate the sample variance of the samples data instead of the populations. So the difference between the sample variance and the population variance is that the sample variance actually take considerations of the degree of freedom. So it would divide it by n minus 1. So in this case, which is 5 observation, which is 5, n equals 5. And we minus 1 degree of freedom, which is going to be 5 minus 1. So we have the degree of freedom equals to 4. So that's why the number is larger in this case comparing to the previous. So you might actually ask the question, so when are we going to use the population calculations and when to use the sample calculations? To be honest, most of the time we are dealing with sample data. So I would say if you are going to calculate the variance of a data set, in most cases, using the variance equation from base R should be sufficient. Well, another measures of variability is using the standard deviations of the data. So the standard deviation, it's basically just the square roots of the variance. So in this case, you can actually use the square root functions here, sqrt, and you put in the variance that you calculate earlier, or in this case, you can actually put in just VA into these functions. So as a populations calculations. So you will get 2.059. Or if you want to actually calculate the standard deviation for the sample variance, you can actually do square roots of VARx. So this will return a standard deviations of the sample variance. This is going to be your standard deviations of your population variance. Well, again, there is a functions in base R that helps you to get the results much quicker. You don't have to do the square root. Instead, you can actually just pass in your data sets into a function called SD, which defined as standard deviations functions. And you run this, and you compare this result to the previous two. And you will notice the SD function actually returned the standard deviations of the sample data, but not the population calculations. Because if you have a population calculation, you should have the standard deviation equals to 2.059, but it returns with the one that's same as the square root of the sample variance. So just note those details. I think it's going to be helpful for you guys to get to know the difference between the two. So let me just denote here, this is n minus 1. Well, doing some measurements of the central tendency and variability of your data is going to give you an idea of how the spread of the data and what is the central point of the data. However, sometimes you might actually want to just get into the data and trying to see what the data actually structure. So to do that, we don't actually have to do the central tendency calculations or variations calculations one by one, because in R there are some very nice functions that you can use to get those measurements. So for instance, you can actually get a statistical summary of the data by using the summary function here. So you can actually click on summary and put in your data sets and run this. Well, this summary function is going to break down the very nice quartiles measurements to you. So it reports the mean values of your data, the median value of your data, and also the quantiles values of your data. So that gives you a very nice structure of your data breakdowns. Well, this is the summary function for your continuous variable, which is the numerical values data. If you have a categorical data, for example, the finalist data sets, and if you use the summary functions, it will return the frequency of each of the class in your categorical data. So pretty similar to your table functions earlier that we've seen. But those are very useful summary functions, and later on you are going to use this a lot, because when you're dealing with like a data frame that has multiple columns, it actually allows you to get the summary of all the columns in one nice table. So to summarize the data frames, I'm going to basically use this data set here called clinical trials in the data folder. I'm going to load this, and I'm going to see what is being stored so far in our global environments. As you can see, I initially have these two data sets to begin with, and I start building different variables, right, to store the medians, means, variance, and so on. Well, I just install this or load this data of clinical trials to R, so you can actually see how the data set look like by using the head functions. So the head function will print you the first 6 observations in the data sets. So in this data set, you have 3 columns. The first one, placebo, drugs, NSAID free drugs, right? So it's basically by categorical. And you have the therapy columns that define whether the person accepts the therapy or not. And then you have the mood gains columns, which define the score of mood gain. So in this case, I have some categorical variable here by the first 2 columns, and I have some continuous variable here on the 3rd columns. Let's try to use the summary functions to see what returns by passing in the whole data sets into this summary functions. Well, as you can see, when I'm using a summary function for a data frame, right, that has multiple columns in there, it returns a very nice table that summarizes all these columns into a very nice format. Well, to actually get a aggregate summary, for example, you want to get the means of certain values by category of groups, you can actually use the aggregate function here. So R has an aggregate function that allows you to break down the statistical summary by groups. In this case, what I'm trying to do here is to calculate the mean of the mood gain based on which drugs the person actually take and what therapy the person actually take. Again, if you look at the data, there's only a category under therapy, no therapy, and CBT. There are 3 categories of drugs: placebos, NSAID-free, and diazepam. So if I'm going to run this, right, I'm going to define the function we are trying to do is the mean functions. It will return a aggregate table here where the variable break down into the first column by drugs, For every drugs, it defines what therapy the person takes, and the third column will return the mean value within that particular category. So in this case, for people who are taking placebos and taking no therapy, the mood gain will be 0.3 on average. And people who are taking this NSAID-free drugs with no therapy will have an average mood gain score of 0.4. The person who take the joint pen with CBT therapy will have an average mood gain 1.5. So this aggregate function help us to do some aggregations of the data and categorize them into different groups to see how each group might behave differently. Well, you can actually apply the same aggregate functions and trying to get the standard deviations for the same purpose, right? So in this case, instead of the mean value, I would like to get the standard deviations of the mood gain under these two categories combinations. So I run this, and there you go. You can see I get all these variations, right? The standard deviations by each group's category defined here. Well, finally, you can also use the Crosstab Functions to actually get some very nice descriptive summary of your data. So for example, I can actually store a Crosstab table by using a table functions and put in the drugs data and the therapy data. So to call out a columns in a data set, you have to first use the data set name and use the $signs to identify which column that you want to use in these functions. So in this case, I'm trying to use the drug columns from a dataset clinic.trials. I'm going to basically create a crosstab table with therapy against the drugs. And I'm going to save this into a variable called crosstab. So I run this. And let me just print out the table here. So now it returns a table that actually show you the frequency of each groups by category. So for example, for people involved in this study who are taking a placebo drugs with no therapy, well, how many patients are in this or observation we get in this data set, which is 3. So how many observations we have from people who are taking the NSAID-free with treatment CBT? Well, we have also 3 observations. Well, instead of using the table functions, you can also take advantage of the margin.table functions and by passing in the crosstab tables that we just created. So this will show you the frequency by the sum over the therapy. So this one right here basically indicate which variable you want to actually summarize in this functions. So let me just run this and see what it returns. So if you're using a margin table here and you pass in the whole crosstab table into this functions, so basically I'm passing in this table here. So it will take the first column right here under therapy and trying to show you the frequency of all the rows here in the category of placebos, NSAID-free, and joyzepam. So it will sum the number of the two and return the frequency for each drugs. So therefore, you will have 6 observations for taking the placebo, 6 observations taking the NSAID-free, and 6 observations taking the joyzepam. You can do the reverse by taking the horizontal axis here. So before we are using the horizontal axis, now I'm going to see, well, can I actually sum up the number by the vertical axis here in the table? So I'm going to define, I want to use the second axis. I pass in the crosstab here and do the summary. So in this case, I'm getting the sum by the observations in the row. So I can get the total observations in the data that takes no therapy, and total observations of the numbers for taking the CBT treatments. Well, instead of doing the margin table, you can also create a proportion table to see how it compares across different variables. So for instance, if I want to use the proportion tables here function, the prop.table functions, and I want to summarize over the vertical rows of rows of variable. So here you can actually see I can actually summarize how many or what is the proportions of the data that actually compare to the total number of placebo takers. So 50% of the people who take placebo actually take the therapy, no therapy, and 50% of the observations who take placebo, they are under the CBT treatments. Well, same for the other, because well, we have all the observation equals to 3, as you can see before. If you use the parameter here 2 to define the probability, the proportion table, you are going to see, well, under no therapy, well, how many observations actually taking placebos, right, in proportions. So 33% of the people who take no therapy, they actually given the placebo drugs. 33% of the people under no therapy taking the answer-free drugs, and 33% of the people under no therapy taking the joystipin drugs. So those are very, very nice Crosstab functions that you can actually use and apply to get a descriptive summary of your data, or maybe getting some insights of your data. Well, finally, if you want to actually get a nice Crosstab table with some structure, you can actually download or load up this library called the DESCR library, and trying to run the functions of the Crosstab functions here. So let me just load up the library, and I'm going to run the functions here. All you need to do is to pass in the 2 columns of data into these functions, and you define the label for the x-axis and define the label for y-axis, and you can run these functions. As you can see, it prints out a very, very nice Crosstab table here with the name on the y-axis and x-axis, and also it gives you the total sum of these observations for each category on these 2 ends. And the Crosstab functions from the DESCR package also returns a very nice graphical tables here, or graphical demonstrations of the deviations of the tables. So I think this will summarize the basic use of these functions in base R and some external library that you can use for a statistical summary or statistical descriptive statistic analysis. In the next video, we are going to look into some visualization tool so that we can actually see it in a graph and trying to figure out what are the visualization tool it's good for the categorical data or the continuous data. Well, I hope you enjoyed this video, and I'm looking forward to see you next time.